Daniel Aliaga is an associate professor of computer science and the co-founder of the Computer Graphics and Visualization Laboratory in Purdue CS. He holds memberships in more than 80 program committees and has several multidisciplinary collaborations and more than $40 million in grant funding. So he'll be talking today about deep generative modeling of urban spaces.
Thank you, Rajesh. And some of that work is actually with Rajesh. So he's also guilty of some of these things that we're talking about here. What we're talking about, we've been doing urban modeling and making better buildings in cities. And the digital twin there has two aspects. One aspect is creating a digital twin of cities so you can do urban planning stuff. And the other part, which is the generation, is it's actually quite hard to get information about urban environments. So we also want to find a way of generating it that's not just the brute force answer. So as a short story, I like stories, but I won't give you too many. One story was I was at some urban conference some years ago and I ran into somebody and they were from New York City working in New York University of some name. And, they say, oh, I want to do this generation and inference. And like, oh, well, why do you do that? I mean, we just go around the city we got a $100 million grant. We have all these toys. We scan every building, every room, every person, and eventually we'll know everything about New York City. But I said, that's the brute force answer, right? I mean, yes, you could do that. And then I asked her, what happens in 5 years with New York City? Of course, New York, we're developing, we're changing things. So in 5 years, are you going to do this whole thing again? I don't know, we might have another grant. Well, okay, how can we do this without assuming you have a $100 million grant to capture one city in full detail? So that's kind of the motivation where I'm coming from. So first of all, cities are complicated places. Maybe this was a city a few thousand years ago, right? And then less thousand years ago, a few hundred years ago, Machu Picchu. But today, cities are pretty complicated places. So they're not simple environments we can just model in PowerPoint. If you look back at urban planning, the way people kind of made decisions about the city, in the 1500s, the Spaniards had a magic formula. They said, we make a plaza, we put a palace next to it, a church, a courthouse, a prison, and then we cut up the rest and give it out to the rich people. That was the formula. And if you go look at historical plans, that's actually what they did, right? That was urban planning in the 1500s, right? Doesn't really work today. We can't really do that anymore. We look at number of people, right? So number of people historically, way here at the bottom. We look at the last 100 years, look at number of people. They've grown a lot. So we have this problem today. There's suddenly lots of people. And that causes problems like urban sprawl in India and other places. Of course, traffic jams, pollution, flooding because people go where they shouldn't, and maybe the climate's changing, all these complicated factors, extreme weather. So these are things that we have to deal with today, a lot more than 100 years ago. Here's another detail. Most people do not live in big cities, they live in small cities. Here is the US. Of the 20,000 registered cities and townships, 16,000 are 10,000 people or less. They do not have $100 million grants for each city, right? That's where most people live. In fact, the big cities like in New York and all those, that's just 10, right? Most of them are down 25,000 and less. So most people do not live in metropolises. We go to Europe, same thing. So the white bars on top are the big cities. So most people live in smaller cities. So therefore, greater than 80% of the people living in cities are not in big metropolises. You might have heard more than half of humanity lives in cities, 60%, give or take, depending which report you read. So therefore, large metropolises might be data rich, but most cities where most people are not data rich. So how can we help them? That's kind of the emphasis. And there are tools around there that allow us to gather information about cities of various sorts. There is, of course, some types of satellite. This is one we like using, Planet Labs, right? It has some resolution. You can't quite make out that's my dog on the roof there, right? It's not full detail. Then, Other companies, Maxar, Worldview, get a little more resolution, still not quite enough to see from the ground view. So there's still some issues. Maybe you get aerial and ground view images, which have better detail, but less coverage, right? You can't take a picture of everything from everywhere. There's also crowdsourced data, OpenStreetMap, and other things that get some information, and maybe some people modeled this part, but they did not model here because, nobody cares about it. So there is missing data in these different data sources. So that's the missing link is we want to use AI in a sense to build or create such information. So from a little bit, we want to generate something, code, program, synthesis, that allows us to get the full details. So even though we only saw this limited amount of an urban structure or building, we actually want to see the whole building and all the detail. How do we do that? That's kind of our methodology. So we want to generate something which is statistically similar to the fraction of the city that we can see, using whatever's out there. So crowdsource, capture data, whatever we get our hands on, we're going to use it, but because it's not captured, we're not going to say, oh, sorry, I can't do that. No, we're going to make something reasonable. And that, gives us something that we can, I don't know, there's a pointer here. We can see more than we can see, right? That's kind of the end goal. All righty. So we have done a bunch of projects, have done, are doing, will be doing projects. So I'm going to just give you some snapshots of a few of them. One of them is this idea where, if all we have is some satellite image like this, we want to figure out where are the building footprints here. So rather than say, oh, we do the best segmentation, super resolution possible, which gives us some limited information, we obtain something like the top there, which if we compare to ground truth is quite good, we think. And the way we obtain this is we actually merged in satellite information, population information, urban rules about how a city kind of functions. So not just picture data, not just pixel pushing. There is actually some semantics and some process modeling involved here, and we get much more closer to ground truth than just looking at that. But effectively, we've done building footprints. Here's just some more examples, comparing it to many other approaches, many different recent methods, and so forth. So the short version is that we're 5 to 50% better than other methods. So this is exciting work, and this is very recent work, and we're still progressing on this. All right, another one is another solution to go through the snapshot. And there's no clock here, right? So I'll just keep on talking. Okay. Huh? Oh, wow. Okay. So what about a city? So here's another idea where we have some information about a city. We have some satellite information. We have some population information, something a land scan project. This is a national project, tells you in every square kilometer of the world how many people live. Some way of obtaining that approximately. Some Japanese data set about terrain height that's very rough. Together satellite, we're able to produce some type of a city approximation like there, which if we compare to Google Earth is pretty reasonable. Right? We generate the whole city scale here. We compare it. We got statistics. It's about 5–10% error compared to reality from very coarse input information. Another project is if we go more like ground view, if we take the best satellite out there. So I was in this project with a bunch of big universities competing with other universities, funded by the CIA. I can't tell you what we did, right? IORPA to be precise. And they wanted to reconstruct any building anywhere so they could do stuff, right? So how do we get a perfect ground view of a building from anywhere from satellite? That was kind of the goal, right? And so this is the best. This is what we do if we just take the best satellite out there and we project at the top. We see this type of stuff, right? So low resolution, trees are annoying, etc. So we developed some technology here to figure out from this how to get the right side, right? So from this input, we produce this and the other examples you see there, which are much better and cleaner representations of reality. So we kind of got rid of these resolutions and occlusions. Another project. Another one about roofs. So this one we actually did a part A, now we're doing part B. Part A was finding roofs in an automatic way. So roof geometry is actually pretty hard to determine. To know if it's flat or non-flat is easy, but actually knowing the roof geometry is hard. So the left is an actual satellite. The right is actually synthetic. So you can't tell a difference, then we succeeded, right? But the right is actually synthetic roof, so we know everything about it. And the next step here is solar energy and estimation and things like that. Here is this picture from the beginning from a single view of a building. We obtained all the way around the building. This is some earlier work that we did that was very exciting, and we kind of, it pushed us forward. Now I want to talk about something which is more related to what Songling was saying before about trees. Here in this work, we want to find individual trees. So I can ask you, where are the trees here? How many trees are there? Anybody? 7. Okay. No, there's more than 7 trees, right? And so, you know, here we obtain accuracies of 87 to 97%, more or less, over a variety of initial cities that we tried. And now actually we're expanding this method to 320 US cities. And I haven't told Songling yet all the details, but in our first test, we seem to be already achieving similar accuracies, and we're comparing this to some Google product, and we're beating out on Google, and we're using this imagery and not Google Street View, which of course is more high resolution, but it's harder to get Street View than it is just to get a satellite image. Satellite is, you got it. Street View, you got to drive everywhere and get it, and trees change, right? So the way this works is we actually look at a 12-month, so a year long of information about trees, and then we perform a segmentation. Then we use some GAN, some generative adversarial networks to kind of seed where it's most likely the trees are. Again, we make use of some knowledge we have about how cities work, because city is not a forest. Trees are not placed arbitrarily. There is logic between those. You have trees in your front yard, your backyard, along the roads, parks, and so forth. They're all patterns, actually. You rarely put a tree in the middle of the road. You can have an island in the middle of the road where there are trees, but not arbitrarily. So these rules we actually can observe from the data and use this to improve the assumption or presumption of where the trees are. And then we get the results that you saw. And now I say we're doing this about 330 cities, and it's not done yet, but this is working out very well. And about compute time, somebody asked. So here we are making use very generously of Songling's cluster. We use it all we can, never stop using it. It would take us about a month to compute the answers right now, which we're not doing on a regular basis because other people want to do things. So we do small little test sets. So it will be wonderful. At some point, we will have to use a month of compute and do a one-time compute answer. And that's great. But, you know, as you know, how research works, we don't want to do it once. We got to do it more times because we figure out things go wrong and so forth. So we're working around this by doing subsets and so forth. But already we started try doing it, and it turned out to be a month computing, maybe 3 weeks if it doesn't crash too often, things like that. But that's about where we are in compute time. Another one that's related is we also want to generate urban layouts. Urban layouts is kind of a 2D plan of a city. So the idea is maybe all we have is this on the left here. We have the roads and those buildings. How do we generate the rest of the city? So that's what we're doing here. And we've generated the right-hand side. In fact, we've generated a bunch of cities where, thank you, where we can generate the whole city from a small fragment, the 2D layout. So this is 2D view of the city. And we have another network that does this using graph-based networks. We're applying it to the same 330 cities so we can generate the whole city from a fragment. Why is this important? Because then, of course, we can generate the whole city. We compare our data to real data. It's very similar. Statistics are wonderful, are very accurate. Another month of compute time to do this. And we can apply this, for instance, for urban planning applications. Here is Chicago, which there is actually OSM ground truth for Chicago. We don't really degenerate it, but it's one of these metropolises, right? So therefore, we take 5% of Chicago and we generate the whole 100%. We compare that 100% to ground truth, and it's quite similar. With very small errors. We have numbers on this. And why do we care about this? Because then we could do, for instance, weather simulations and compare the weather with only knowing a small amount of information about Chicago. But of course, we can do this for any of the 320 cities, or any of the other 16,000 smaller cities would be the idea. Well, what about cities that used to be, right? About archaeological sites. So we have a branch that's going out and thinking about this in archaeological sites. So this is a city where we've site archaeological, and we've done 2D completion of this. And we're looking at other sites, even in Greece, that are very incomplete. And then maybe what we want to get to is something like this, where this is all that we see. How do we automatically create something on the right? What this archaeological site used to be. This is created by a human, by archaeologists with like inference, but how do we automate this? So we're en route to try and make this happen. All right, order applications, so weather, flooding, vehicular traffic. I really get the signs, so I'm going to go quickly. This is what I said about the weather simulation. So maybe it's just important to see all these look about the same, and that means that with only a fraction of the city, we can simulate the weather well. With only the fraction of provided data, we infer the rest. We infer the rest of the digital twin, and we can perform a full weather simulation. We've done cloud control, so only from a portion of the city, we generate the whole city, and then we can do what-if scenario planning. We can rearrange parts of the city and see how the weather, the clouds would change. Temperature mitigation, how the temperature would change. Again, since we have a digital twin of a city, we can do all these urban planning applications very easily. So temperature mitigation, greening, if we do greening in different ways, it also mitigates changes the local temperature and wind patterns. And flooding also, since we work with some people in Belgium, in Europe, and there's in Northern Europe, a lot of flooding is important. 2 minutes, okay. And so we want to determine which urban planning parameters are important to passively reduce flooding. Flooding you can reduce, of course, by big walls and canals, and that's wonderful, but also a new trend is to design the city in such a way that if it were to flood, it would be less impactful. So here we determine which urban planning parameters are beneficial. Again, since we have access to the detailed plans of whatever city, almost whatever city we want, we can study this in broad scale. So about a dozen cities were studied for this. Urban traffic, also we've done some stuff and so forth. Anyway, so this has been funded by a bunch of people, and kind of like Song Ling said at the very beginning, it's not just me, it's a bunch of people over the years been working on this. I'm just here talking about it, but I welcome any suggestions and of course opportunities for further things to investigate. Thank you. Thanks so much.
Yes, I think it was your solution 4 event, the one where you were really excited about taking just a snapshot, being able to like generate a full 3-dimensional representation from, just infer what it is and get rid of a lot of the occlusions and whatnot. The output of your model there, is that just a nice picture that it puts out, or like
No,
what sort of
geometry?
So it's like the full geometries
Yes.
that it can
It's a
predict.
3D model in whatever format you like.
Awesome.
So I'll ask one more computational question. So you said that 80% of the people are living in smaller cities. So in terms of computation, like what's the computation ratio? Like large cities are obviously more complex, so probably taking up more of your computation than the smaller cities.
Yeah, so if you go by surface area, something like that, that might be a way of doing it. I don't have those numbers in my head, but it's not the case that the large metropolises or most of the surface area of cities. No, that's not the case. But I don't have anything more specific than that.
Thank you.
Yes, Carol. Oh, all right, and somebody else.
So I'm wondering, so you're doing these, what do you call it, modeling? You come up with, one city at a time.
Yes.
And I'm wondering if you have examples where you want to, as you said, cities change and trees grow, people move, all those things. So I wonder if there examples that you have that you want to do like a really large calculation at once? Are there some of those examples? I can understand you can build,
Right,
piece by
so,
piece.
I mean, a potential thing which we've only thought about is that we could do these 330 cities today and 10 years ago and do a delta. And so that would require a few months of compute time, right? Now, how often do you want to do that? I don't know. Probably some of these things don't change on a daily basis in a significant range. There is, of course, from the point of view of worldwide, some desire to do daily monitoring to see what's happening, obviously deforestation, things like that. So change detection is a field and that will require frequent recomputing.
Can you combine that with climate simulation outputs, stuff like that?
Oh yeah, so all this what we want to do is one of the major things we do is output this and run it with weather and climate simulations, which is not the same thing. So
Yeah.
that's definitely, so, Dev Niyogi in Austin, this is what we do with him still, trying to improve weather and climate prediction.
Okay, thank you.
So tying this back to the fundamental concepts of digital twins, I understand that a lot of digital twins requires data to be sent back from the physical object to the digital twin, so as to make it more comprehensive per se. So what are the kind of metadata that you associate with digital cities? And what are the telemetry that you collect from the physical world, and how do you tie it back to the data to augment it?
All right, great question. So I don't have a very concise list, but kind of whatever you got, right? So, sometimes people's a whole group's research is about one city. So they'll get lots of information about that one city that was somehow collected through a multimodal process, humans, computers, scanning, whatever. And that can be done, right? That's very painful. So we're trying to enable is that, how to achieve something similar to that without having to assume you manually require and put this together. So it's a completion process, a generation process. So we've generated like facade level details where there was no pictures. We've generated window level details where there was no window data, right? We've generated footprints where there was no footprints, that type of thing. And we have not addressed the interior of buildings yet, right? So that would be another level of detail. So I think you should more think of it as whatever you have, we can start with, and we'll try and generate more of that to complete the picture. So we don't assume that everything is there. We will actually try and complete it. That's kind of the goal. So for the flooding work, it was different type of information than for the footprint work, than for the facade work and so forth. I hope that helps with your question.
Well, thanks again, Daniel. I think that's all the time we have questions, but
Thank you.
stick around if you can.
I'll be around. Thank you.
Thank you.